Welcome to Scientific Software Horizons, the podcast where curious minds in science and technology come together to explore what's next for scientific software. Each episode brings you into the conversation with cross-disciplinary experts and community visionaries as we dig into the opportunities, challenges, breakthroughs, and emerging solutions shaping the future of scientific software. From HPC to AI to quantum, we're diving into the technical leaps and the human stories behind them, the people, the practices, and the evolving ecosystem driving tomorrow's discovery.
As the noted moral philosopher Samuel Johnson once observed, the friendships which are to be continued to old age are rare. Now, in our professional lives, that may be even more true. Not many people have the good fortune to remain connected with colleagues for more than 3 decades, especially colleagues who have become industry legends with worldwide recognition and credentials that age smoother than a barrel of Tennessee whiskey. It's my honor to formally introduce a gentleman I've seen every year since 1988. That's 38 consecutive years of attending what we now call the SC Conference, originally known as the Supercomputing Conference. Now, along with a small group of colleagues, we've shared that tradition year after year, eventually earning ourselves the affectionate title of the SC Perennials. Why? Well, because like perennials, we keep coming back. Over those years, I've watched his name and accomplishments rise in tandem, culminating in a global reputation defined by his deep expertise, unwavering commitment, and the profound respect he commands throughout the scientific computing community. Our guest for episode 1 of Scientific Software Horizons is none other than Jack Dongarra. As most of the world knows, Jack specializes in numerical algorithms in linear algebra, parallel computing, and the use of advanced computer architectures, and the programming methodologies and tools that power today's parallel systems. To put it simply, if you exist anywhere in the scientific computing universe, you know who Jack Dongarra is. We're honored to have Jack join our hosts, Mike Heroux and Lois Curfman McInnes. And now to bring Jack onto our virtual stage, here's our co-host, Mike Heroux.
Thanks, Mike Barnhart. Jack, it really is an honor to have you here. Recently, you co-authored an essay published in Cloud Computing for Science and Engineering with Dan Reed and Dennis Gannon. The title was Ride the Wave, Build the Future, Scientific Computing in an AI World. In that article, you argued that AI is not replacing scientific computing, it's reshaping it. Simulation and data AI are converging, and the future will belong to those who understand how to integrate the pillars of this ecosystem. So today, we're going to use that essay as our launching point. So just to kind of start us off, in this essay, you describe AI not as a disruption to scientific computing, but as a wave we should ride. What does riding the wave mean in concrete terms?
Right. So it's a catchy title, Ride the Wave. It means a changing reality that we have. AI has shifted the market, the roadmap, and even access to leading accelerators. Scientific computing can't wait for the old, what I'll call 64-bit centric systems. It must thrive on AI-optimized platforms by adapting algorithms, metrics, and procurement strategies. But Ride the Wave is only half. We really want to build the future, of course, which means investing deliberately in new foundations. And by that I mean energy-aware algorithms that are designed end-to-end workflow benchmarks that have a software stack that's optimized for joules per trusted solution. Not just we followed flops for a long time, and we still need to keep an eye on it. But the new metric I think is going to be joules to trusted solution. So how much energy are we using to solve our problem?
So would you consider this moment comparable to, say, the transition from, vector multiprocessors to distributed memory systems?
Well, the only thing constant in high performance computing is change. And yes, absolutely. So, we went from vectors to adopt microprocessor based massively parallel systems. And that change was brought about because the economics didn't make sense for vector computers going forward. That is, we couldn't pay for the kinds of machines we wanted. We had to pay for the machines that could deliver potentially the performance, but were different. So I say yes, it's the same sense as mentioned in the paper. Every major transition is driven by market forces and semiconductor economies, and those that fall short really fall behind. But the shift is broader. It's not just parallelism. It's AI driven this time. AI precision formats, software ecosystems, and platform controls. So I would say, it is similar to what we had before, and we need to adapt to that changing landscape. And in some sense, it's, follow the money. That's where the money is, and that's what's going to drive the technology and the economics. And we're doing that by riding the wave.
Yeah, great. Thank you. I think, Lois, I think you have a next question for Jack. Why don't you go ahead?
Jack, your article emphasizes the convergence of simulation, data, and AI. From your vantage point, what is fundamentally new now about this convergence compared to previous eras?
Right. So in the paper, we talk about these maxims, and maxim one is that modeling and generative AI are now peer processes in discovery. So it's not just simulation plus a little machine learning post-processing. That's been going on for a while. It's now integrated into the workflow. We have surrogates with verification, data assimilation loops. We have hybrid PDEs that learn with learn closure, and pipelines where induction models and deductive physics inform each other continuously. So it's really an interplay, a convergence between those inductive models and deductive physics that we need to focus on in going forward. It's the same, and some of the same issues are there that we faced in the past. So by that I mean we got to be aware of bandwidth. So bandwidth really dominates any kind of issues on any performance. So the paper argues that energy and data movement, not flops, are the scarce resource. And we've sort of known that for a while, but now it's really coming forward. And data movement can cost more energy than arithmetic. And that's why we're proposing this joules per trusted solution as a metric that aligns with reality. Numerical linear algebra evolves because of AI workloads. So we have hardware that's evolved for AI. We look at reduced precision because that's where AI lives. We have tensor cores that are really matrix multiply engines. We have memory bandwidth trends that we have to focus on. And the paper highlights some of the issues with mixed precision broadly, in using mixed precision for correction certification and low precision for bulk work. That is, use the high precision for the correction certification and the low precision for the bulk of the work. We have a terrific set of tools that have already been developed that help here. Iterative refinement for linear algebra, and also inner and outer iterations where we can exploit mixed precision. We have stochastic rounding that we can use, randomized algorithms. There's this wonderful example of matrix multiply that our Japanese colleagues, the Ozaki algorithm. And that allows for integer arithmetic to do simulations for floating point, and allows much higher rates of execution. But I want to temper that by saying Ozaki is great for matrix multiply and for large matrices. If you're below, I don't know, at 1,000, it's not going to pay off. And if you don't have matrix multiply, it's not going to work. So matrix vector doesn't work. Vector operations and scalar doesn't apply to Ozaki. And that's because of data movement. There's too much data movement with Ozaki. With matrix multiply, we have that wonderful surface to volume effect, n-cubed operations and n-squared data movements that we can leverage. And that's why it's a winner. So I think those are a number of things that we that we need to keep in mind as we go forward in this way. Things are changing. We need to apply a different set of tools. We can do that, of course, and it's just going to be it takes time to adapt.
Thanks, Jack. Just one follow-up on this topic. What personally excites you the most about this convergence from a
Okay.
scientific perspective?
Yeah. So this is a great time. I mean, we have AI, which provides this incredible space, and then we have our knowledge of high performance computing. So it's a credible hybrid loop. AI surrogates to explore parameter spaces quickly, then high fidelity simulation to verify. So that's an important step, of course. Plus AI assisted adaptivity for mesh refinement and mesh refinement prediction. The paper cites an example for weather and captures the promise and some of the limitations. AI can be very competitive on standard metrics for a 10-day forecast. It can even beat the existing numerical simulations that we run when trained for long reanalysis. But the physical HPC still matters, and it matters because of rare or extreme events are outside of that training distribution, and AI just can't pick it up. It's the example, I guess, would be for tornadoes. So tornado is a rare event. It has certain conditions which can't be captured by the all the data that AI has to analyze. So we need something else to help us in that sense, and that's where the physics-based computations come into play.
What does correctness mean, when models are, fundamentally probabilistic? And, in particular, are we moving away from deterministic approaches towards something that's more statistically oriented?
Well, I think classical methods will persist, but they'll be wrapped in a hybrid workflow and implemented with mixed reduced precision plus explicit certification. So we need to maximize throughput on AI hardware while preserving trust. So, hybrid methods, physics-informed machine learning and AI accelerators are great things. And, the paper gives some concrete examples about surrogates and with verification, learning components inside of data assimilation and inverse loops, hybrid PDEs plus learning closure modules as benchmark-worthy workflows. So these things, mixed precision and optimization is going to be front and center. There's a paradigm shift that's coming. The paper frames it as a core lever for reducing joules per trusted solution. Most of the work in low precision that runs fast using, those tensor cores, those matrix multiply units, then correct and certify the high precision residual checks, iterative refinement, stochastic rounding, randomized sketching, wherever appropriate. So there's really a combination of things here. And, the paper looks at what it means to have correctness in these probabilistic models. Correctness becomes an explicit acceptance test at a declared workflow boundary. So we have residuals, backward error, conservation checks for simulation. We have forecasting skills, reliability, diagnostics for machine learning, and that's all going to be put together to give us an end-to-end quality measure for these coupled workflows.
What architectural trends do you believe will most impact scientific software over the next decade or so?
Right. So the biggest impact are driven by energy and memory. So deep memory hierarchies, heterogeneous accelerators, and designed optimized for low precision and high bandwidth. In the paper, there's a table, and the table is a simple warning in some sense. AI-oriented accelerators push floating point 16 and integer 8 operations. That's what's used to drive the machine learning AI algorithms. And throughput, in terms of 64-bit floating point, is growing slowly, and it's a real system constraint because of memory bandwidth and data movement. And that forces scientific software to be bandwidth and energy aware. So the table shows 3 generations of NVIDIA products, from 2022 Hopper to 2024 Blackwell and 2026 Rubin. And what we see is that 64-bit tensor core with the early one, Hopper, is at 60, the peak is at 67 teraflops. And Blackwell, it drops to 40 teraflops. And Rubin, it drops even further to 33. So new generations have less floating point potential, 64-bit floating point speeds. And, that's a result of the architecture and the room on the chip not being spent to do floating point, but not being spent for 64 floating point, but being spent for other operations. So just in contrast, the 16-bit tensor cores on Hopper were at roughly 1,000 teraflops. When they went to Blackwell, it was about 2 teraflops. And now with Rubin, it's 4 teraflops. So you can see that increase, doubling every couple of years in terms of the performance. The same thing was true of integer 8. So that's an interesting case. So in 2022, the integer 8 operations, the tensor cores, were about 200, I'll use the word tops now. So not teraflops, but operations per second, to 2,000 teraops in Hopper. Going to Blackwell, it went to 4.5 teraops, and going to Rubin, it dropped to 250 teraops. And that drop was precipitated by integer 8 not being focused on in terms of AI applications. They're switching to bfloat 16 operations. So again, the decision was made to reduce the amount of area on the chip for integer 8 as well as floating point 64 to accommodate what's important for AI applications. So that's I think it's an interesting case where the hardware is adapting quite rapidly to the changes that are seen in the market and what's driving those changes. Fortunately, the bandwidth numbers go up. So it went from 4.8 terabytes per second for Hopper to 8 terabytes per second for Blackwell, and now with Rubin we have 22 terabytes. So that's something that'll help all applications. Bandwidth is the thing that really matters.
Indeed. So I guess a question from a scientific software point of view is, how should we as developers of scientific software think about portability given these architectural complexities and heterogeneity?
Well, portability is key, of course, to having a life beyond the current thing. So portability must include things like metrics and trust, of course, not just performance. The paper calls for a software stack that exposes precision modes, tracks provenance, and reports energy data movement. So we need to do more of that, I think, in our applications and our benchmarks, so that we can compare designs and keep workflows reproducible across those platforms. So portability is central to the way in which we should think of any kind of scientific software going forward.
About software ecosystems, the sustainability. So you speak not only about technology, but also about building the future. And what role do software ecosystems play in making this transition successful?
Right. So it's critical, right? So the paper argues that the transition succeeds or fails on the software ecosystem. If the market churns hardware and platforms, scientific productivity depends on reusable libraries and stable tool chains and workflow level infrastructure that can absorb changes. So building the future really, in some sense, means treating curated data, training models, and software stacks as long-lived infrastructure. And that should be on par with the compilers and linear algebra libraries that we've grown up with. So, it's really an important issue, the software ecosystem itself.
So, what role do the labs and universities have in that? Because if I look at industry as such a large budget for these kinds of investments, say relative to at least historic funding levels that labs and universities have been able to provide, what's the relationship between these entities, organizations as we go forward?
The labs and universities play a critical role in terms of feeding students and producing the next generation of scientists. there's an important to share library. It's important to share library and standards. So we need to come up with ways to develop those libraries and put in place the standards. And it really requires not only universities and labs, but also industry to take part in that. And there's some really great examples. So MPI was done along those lines. That is, it got together, I'll call them leaders in the from the universities, the labs, and also the vendors to get together to describe a message passing infrastructure that could be used that will allow portability across different machines. So building up that software ecosystem, and the result of that was immediate adoption and the ability now to develop software that has a life. So we enjoyed that with the linear algebra software that we developed. Another example would be the BLAS. It has a similar sort of trajectory of getting the community involved in developing this standardized set of routines that could be used. I think we need more of that. So what I would advocate is that we get together with the community to develop a set of low-level routines like the BLAS for AI. And not only for AI, but I'll use the other word, the quantum, for quantum computing. There's a set of routines that are going to be critical for the portability of models that are going to be built in AI space and also in the quantum space that we should contribute. We should be part of that process. We have tremendous historic information that comes with us in putting these things in place. And together with the leaders in industry and vendors, we can, I think, develop. So that's an important thing. The thing I worry about with all of these things, and especially at the labs, is that issue of sustainability. So we develop algorithms and software. They get put into applications and they get disseminated to the rest of the community. And there's no real mechanism, no persistent mechanism that's in place to help with the sustainability of that software as it was developed. And we need a process, I think, that makes it a bit more rigorous. There are certain efforts, but I think it needs to be brought up to the front rather than to be in the back of the line. So, I think the paper argues that we need to have some input and responsibility to developing these things.
Thank you very much, Jack. This concludes our part one of the conversation. We'll be back with part two in the next episode.
Well, that's it for episode 1 of Scientific Software Horizons. A very sincere thank you to our special guest, Jack Dongarra. Thanks to our host, Mike Heroux and Lois Curfman McInnes, and our producer, the very talented Justin Breaux. We'd like to encourage all our listeners to please tell your colleagues about this podcast. Remind them to follow us on our Scientific Software Horizons LinkedIn page to get updates on future episodes, special programs, and other activities. Until the next episode, for Scientific Software Horizons, I'm Mike Bernhardt.